Okay, we're going to take a look at the trapezoidal rule and in particular how it relates to an integration question where we might be asked to estimate the area under a curve like this using the trapezoidal rule and then maybe to find the area exactly using integration. Now this we can see this shape here wouldn't be a traditional function that we'd be asked to draw, and so it's unlikely we would have a formula here to do integration, but we will see a couple of questions later where we can integrate the function so that we can get the exact area under the curve. So what's the trapezoidal rule? Well, the trapezoidal rule is a rule in our formula book. It's on page 12, and essentially what it does is it breaks this area up into trapezoids and then finds the sum of the areas of those trapezoids. I'm not doing a great job here, to estimate the area under the curve. So the formula we have that sums those areas together is A equals h over 2 on y1, which is the first height, we can see it here that it's 0, plus yn, which stands for the last height, so the last height here is 40, and then 2 times the sum of the rest of the heights, and that's 30 plus 35 plus 40, 45, 30, 25 and 30. And the h stands for the equal gap of every interval. So every gap has to be the same width. In this case, the gaps are 20. So this is the way it looks in the formula book, but it is worth remembering it as h over 2 on the first plus the last plus 2 times the rest. Very popular question in ordinary level maths where we just plug in the information on the diagram into the formula and we work out what the area of this shape would be. Where they might ask it in a more tricky way, at ordinary level at least, is they might remove one of the dimensions. They might call this x, but in that case they would have to give us the area of the shape and we would have to work backwards or solve an equation to solve for x. Okay, so we'll do a couple of ordinary level type ones and then see how it links to maybe an integration question. So here we have our formula and we have the gap is 20, so h is 20, and then we have the first is 0, the last is 40, and then 2 times the rest. So we pop all of this into our calculator. Sometimes it's worth tidying up or doing a little bit of the work yourself. Particularly, we would have to do this, like I said, if one of these dimensions was x. So it's no harm doing the little bit of working out yourself. But if you threw it all into the calculator, we would get the number 5,100. And again, if this was an x, an unknown dimension, for example, the height of one of them, we would let our formula equal 5,100 and we'd go and we'd solve the equation. Okay, like I said, we can't find the exact area underneath this curve because we don't have a formula for a function, but we will see in integration that's something we will be able to do. Okay, so here's another example. This is from the 2024 Leaving Cert Ordinary Level paper, and what we have here is this does look like a function. There is the graph of a function k of x. Now we're not told what the function is, but we are given the outputs or the y values for various inputs of x. So x equals 0, 1, 2, 3, 4, 5. When we put those into a particular function, we get 12, 9, 6.8, 5.1, 3.8, 2.8 respectively. And so these stand for heights that we can use with the trapezoidal rule to find or estimate the area under this curve. So again, we're going to write down the rule, and this is our short way of remembering it. So h over 2, first plus last plus 2 times the rest. H is the gap, and in this case the intervals are 1, so the gap or the widths are 1. The first height is 12, the last height is 2.8, and then the rest of the heights are 9, 6.8, 5.1, and 3.8. So we're going to pop all the information into the formula, and we can use our calculator just to work it out. That the area that we've estimated under this curve, 32.1 units squared. Okay, in the next part of the question, they ask us to use the formula for percentage error to calculate the difference between the true area, which they tell us is 31.8, something that we're going to work out for ourselves using integration in the higher level examples, and then the estimated area, which is 32.1. So to find percentage error is the error over the actual multiplied by 100. So the error is the difference between the two areas. which looks quite small. So the difference between 32.1 and 31.8 is 0.3. The actual area was 31.8, and if we divide the error by the actual, we can see it as a percentage. It was a less than 1% error, 0.94% error. Okay, so let's take that idea, and then this idea that trapezoidal rule will find an estimation where integration can actually find the actual area, and we'll be asked to find a couple of percentage errors using that same idea. So in this higher level example from 2015, we have a quadratic function. So we know that the shape of this is an n because it has a minus x squared part. And we're asked to fill out this table. Now filling out this table is just subbing in input values 3, 4, 5, 6, 7, 8, 9 into the function to get out the y values or the output values. So we put in 5 and 8 comes out, we put in 6 and 9 comes out, we put in 8 and 5 comes out, and we put in 9 and 0 comes out. And we can see that these y values increased to a maximum and then they decreased again, confirming that we had an n-shaped graph. Now, it says use the trapezoidal rule to estimate this area. So here's a graph of the function, and we can see that for an x value of 3, the y value is 0, and for an x value of 9, the y value is 9. So there are our first and our last heights. We can see that the gap is 1, so our h value is 1, and then the rest of the heights are the outputs when we put in 4, 5, 6, 7, and 8. So we write down our formula, and we're going to put in our values into it. So h is 1, the first is 0, the last is 0, plus 2 times 5 plus 8 plus 9 plus 8 plus 5. And we get an estimation for this area of 35 units squared. So that's an estimation of the area underneath this curve down to the x-axis. Now, how can we find this area exactly? It's not exactly 35. How can we find it exactly? We can find it exactly by using integration. And this is what this asks us to do. It doesn't say it explicitly, but when we integrate a function from 3 to 9, we're finding the area between that curve and the x-axis from the x values 3 to 9. So integrating this polynomial, we have minus x squared. Well, we raise the power and divide by the new power. So this is going to be minus x cubed over 3 plus 12x squared over 2, and then minus 27x. And we're going to sub in the limits of integration then 9 and 3. And when we do that, that'll give us our area under the curve. So just showing when we put in 9 and when we put in 3, these are the values we get. And then that works out to be an area of 36. Now, if you remember, estimating the area under the curve was 35, and now we have an exact area of 36. So there is a small error in the estimation that we would have used before. The question asks, what's that as a percentage error? Well, again, the percentage error is the error over the actual. So the error is 1. 36 minus 35 is 1. The actual was what we got using integration, which is 36. And then we multiply that by 100 to turn it into a percentage error, and we have a 2.8% error. And if we go back to the previous slide just to see where does that error occur, well, when we're breaking this up into trapezoids, so what we're doing, and it's kind of hard to see because the curves, some of them look like straight lines, but imagine a trapezoid coming down here, that's slightly underestimated the area. The next trapezoid has also slightly underestimated the area. There's a piece that we're missing in here that we're not getting the area of when we break it down into trapezoids. Now normally this balances out, but in this sort of a quadratic shape, it's always an underestimation. There, if we get all this of area, we're missing a little piece in here. This area, we're missing a piece in here. This area, a little piece in here, and this area. Now the sum of those bits that we're missing is 1. It's the difference between the true area and the estimated area. But that's why we sometimes don't get as accurate a result. Sorry, just to go back here another second, how could we be a little more accurate in our estimation? Well, we could be more accurate by halving the interval. Instead of it being 1 wide, we could have it 0.5 wide. And when we do that, our trapezoids estimate the area a little bit better. How could you get it even more accurate? Well, we could divide into quarters and we'll have loads and loads of trapezoids. It would make it even more accurate. And essentially what integration does is it finds the sum of all those areas, making the widths infinitesimally small, and so we get an accurate representation of what the area is. Okay, last one. So the last one that was asked, and it's only been asked at a higher level twice, which is 2013 and 2015, was to estimate the area underneath the sine function from 0 to pi. Now, 0 to pi is only half of a period. We know that this would continue to come down and then it would come up again, and goes on obviously like that forever, the sine function. But we're only trying to find the area from 0 to pi. First of all, using the trapezoidal rule, using estimation, and then we're going to find it using integration. So if we first fill out a table to figure out what the heights are, well, the sine of 0 is equal to 0. And make sure your calculator is in radian mode when we're putting in these measurements. So the sine of 0 is 0. The sine of pi over 6 is a half. The sine of pi over 3 is root 3 over 2. Now, as a decimal, because that's what we were asked for, we get 0.866. But if we look up our formula and tables book, we can see that the sine of pi over 3 is root 3 over 2 as a nice surd. And I'm going to put it down here in the table, but obviously the question did ask it for as a decimal. The sine of pi over 2 is equal to 1, the sine of 2 pi over 3 is equal to root 3 over 2, the sine of 5 pi over 6 is equal to a half, and the sine of pi again is equal to 0. So these y values are increasing up to a maximum of 1, that's 1 there, and then they decrease back down to 0. So we can use these as the heights for estimating the area using the trapezoidal rule. So if we write down the trapezoidal rule, and so our informal definition is A equals h over 2 on the first height, which is 0, plus the last height, which is 0, plus 2 times the sum of the rest of the heights, which I'm going to actually put in as the surds, just to have it a little bit more accurate, but you could put in the decimals if you wanted. We're going to throw all that into the calculator, and we estimate the area to be 1.95407 units squared. So again, this is an underestimation. If you think about the trapezoids that we're making, if we make this trapezoid here, for example, we're missing this green portion of it here between the straight or the line at the top of the trapezoid that we would make and the actual curve. Now, how can we make sure to include that area and get the entire area of this between this curve and the x-axis? Well, we would use integration. So if we have a look at integration to find the actual area, it's a very simple integral, and we're integrating the sine of x from 0 to pi. The integral of sine of x is minus cos x, so that's in our formula book. We're going to sub in 0 and pi, so minus cos of pi minus the cos of 0. So we get minus minus 1 minus minus 1, which is 1 plus 1, which is 2. Now remember, before our estimated area was 1.95, an underestimation. The actual area is 2, and then we're anticipating that they might ask us for a question about what's the percentage error. So the percentage error is the difference between the two of them, which is 2 minus 1.95407, over the actual, which was 2, and then times it by 100%. So we get a 2.965 or a 2.3% error. Okay, so important to know the trapezoidal rule. Maybe it would come up in a question, an area and volume question, but more than likely if it comes up as part of an integration question. And important also to know the formula for percentage error.